Hi, this is SYbarra for Game Engine 3, my final demo submission. Um, so, just to go over how this works, I essentially have two branches. I have my main engine that I kept around for safety reasons, and I'm very glad I did that. And then I also have my compute shader engine where I was essentially using it to debug and work out the compute shaders. So let me show you the good news, what I have working. I was pretty happy with. So between engine 2 and engine 3, in addition to the skinning, I was able to work out how to get the instancing working. I don't have any management systems yet, but I do have it where it would be fairly easy to get that working, especially after kind of working that out a bit in audio engine as well. So let's run this. First things first. So as you can see, I have instancing. For these skeletons, what I need to do is go in and reduce the bone width, and then also for each skeleton bone object or game animation object, I need to implement a separate draw method for each of them, and then I can just essentially have it do nothing, so I can get rid of these nasty unicorn things popping out of their heads. But since the teddy is so wide, you can't see his bones at all, which is nice. So let's go through and see what else I got here. So I got a few different angles. So this thing right here, you can barely make it out right here in the middle. Essentially, I feel like that is the root node, and it's just, or the game object rigid, and it's just rendering this origin of the world. So it's a cool little ninja star. It's a feature, not a bug. It's also kind of a nice reminder of where the origin point is. So in addition to my animations and skeletons and stuff, I also have my models running from Engine 1. So I reworked the model files to allow me to still render those in their bind poses, even though they don't have any animations. So that's always fun. So I have multiple instancing working, which I was pretty happy about. Now for the bad news. So in this, my animation controls don't quite work with the instancing, which is unfortunate. I don't think it would be too hard to hook back up, but like I said, we're pretty pressed for time these days. As for compute shading, let me run that system. So here's my compute shaders, and you can see, oh wait, oops, sorry. And my compute shader, what? I think I turned off all my compute shader stuff. Anticipation of this, yep. So either that or my compute shaders are suddenly working. Don't think they are though. Well, let's go over what we have going on here. Oh, you know what? Nope, I know what the problem is. I loaded up 2 instances of the wrong engine. I was going to say there's no way that I'm getting that lucky today. So here's my compute shader engine. There we go. That's more like it. Okay. So compute shaders. I understand what they're used for. Even though I don't have it quite working, I'm still really glad we went through this exercise. Essentially, on a high level, if I were to explain it to my second graders, for example, it's called a compute shader because it's used for parallel processing. So what you want to do is, rather than like we've been doing where we're just iterating through all of our bones, performing a whole set of operations one by one, you essentially just load this up into a nice grid orientation. It works out perfectly because all of the data is parallel, and you can just run all the calculations on the graphics chip all at once, and it saves a tremendous amount of time. So these transformation calculations on the vectors and the quaternions for the translation, rotation, and scale to get the bone transformations and then reflect that in the world space, we're just basically loading in all of the bone objects into the graphics object and processing them all at once. So let's run this, and you can see my epic failures, and yeah, there's nothing there. The only thing that's there is just one game object rigid, and that is because I wanted to just reduce this down to one teddy bear before I was able to get this instancing. So a little interesting that nothing's rendering, but my models are still there, so that's always nice. So what went wrong here? Well, I've been working through this, and essentially what we have going on here is inside of the skinning graphics object, I am creating a separate shader for the compute shader. So I have a skinning object for the graphics calculations. I will, big disclaimer, this is fairly based on Matt Feingold's code. Like I said, once we get this working, it's nice to have a working demo so you can go work in and tweak around and experiment a little bit with the shaders, especially so you can get some of the cool colors and also see what you can and cannot get away with as far as changing the code. That being said, I felt like that was fair game since directories were kind of opened up to everyone. So as we go through this, essentially what we do is any animation calculations that were processed in the skinning, we pass them into the compute shaders. So we have two separate compute shaders. One of our compute shaders basically calculates the local transforms, and then the second compute shader calculates the inverse transpose to do the skinning calculations and then renders that on the screen. So instead of accessing the inverse bone matrices array and the result bone array like we did in our CPU animations, let me go back to that here real quick. Right, so instead of, where is the animation? Here we go. Instead of doing all these calculations with the load animation, we still do that. We essentially just write that to the GPU with the OpenGL commands. We pass it through a GPU buffer object, so you can see I have one right here. And essentially it's got all the functions for the binding the layout, wrapping all of these OpenGL, these messy functions. We push it to the GPU. This carries anything from pretty much actually anything. So we have our buffer data object here. It's a little bit of a header. It's got the number of elements inside there, the size of each element, and this void star data passes in whatever types of data you want to send in. Basically, it could be your bone arrays, your inverse matrix poses, anything you'd like. We write it to there. I had some challenges early on. I'm running OpenGL 4.3. The map buffer data, it's the GL map named buffers that only works in OpenGL, I think 4, 5, and on. So I had to kind of rework things to make it work with OpenGL 4.3. Otherwise, I was getting these weird exception errors. Essentially, I pass in my local result bone array to compute shader 1. And let's jump into that. So we get the VAO of the model, we pass in the projection view matrix as we pass in the stuff to the GPU. Here we are. So inside of animation, we run through our first compute shader. So I'm just inside of each animation object, just to get this working, I was just creating a new shader object when I instantiate everything. I'm basically loading up two shader objects. I'm creating a interpolate, which performs all the local transforms, and then skin local to world. So compute skinning 1, compute skinning 2. Both of these are compute shaders. For standard, bell rings, kids are going to be here in 15 minutes. For my standard models, I process those as graphics shaders, so it still was able to render them the same way in their bind poses. So here are graphics buffer objects. We have a couple testings. We also have the bone world inverse graphics object, as well as the bone matrixy local transforms. So we basically bind those to the GPU and we access them with an ID, like a GL ID. The way I look at it, it's essentially like instead of doing a do-it-yourself project where we're doing all the calculations ourselves, we are hiring a local contractor to perform these calculations, and that local that contractor is the GPU. So when I pass this information to the contractor, he gives me an ID card. So anytime I need to check in on that information or that data that he's working on, I just go up to the desk, hand him my ID card, and I can get that information back. So that's essentially what we're doing here. So for the process animation, as you can see here, for the CPU skinning, I just commented this out. As Feingold did, I liked his method. He broke this up into two different process animations. He has the process the CPU. I wrote here slow just for dramatic effect, and then fast process GPU. You pass in the same data, it's accessed differently. So on the slow process, it's the same old thing we've seen. We do all the calculations bone by bone, pass them to the model. This was a testing section. For the fast process GPU, however, we are, you can see, binding it all to the compute shader 1 to perform these operations. After compute shader 1 completes its operations, we can take a look here at compute skinning 1. It's got the CS to denote it's a compute shader. You can see here's all the information, 430 core, matches up with my versioning. The bone structure, we redefine everything that needs to be calculated since the shader can't access anything externally. We have our animations, we bind everything out to the layout as it says we do here. You can see alert factor, num bones, rigid trans, rigid scale, rigid rotations, everything aligns. We bind our local bone matrices, we've got our two frames that we're going to interpolate through, and we run through. So as you can see, the calculations are fairly similar to how we did them externally, except for this mix calculation that's essentially OpenGL shaders calculation for interpolating between the bones, but you get the picture. So we pass this out through, we pass this to the second compute shader with the bone ID. As you can see here, this is more just math function redefinitions. So once we pass this into the compute shader 2, you can see down here, this is the second phase. So second compute shader gets the inverse bone calculations. Again, we got this from our skinning in the converter from the first part of Engine 3. I was able to get that working on the CPU. Again, the challenge is just trying to get all this lined up on the GPU, but we bind all of our layouts, get everything lined up properly. Obviously, I have something not lined up properly, otherwise this would be working for me right now. And we go in here and we're eventually going to pass this information to the vertex and fragment shaders. So we do all the calculations here. Now, the interesting part of this is how, depending on how you passed out your parent index hierarchy to keep our data aligned, I, inside of the animation converter, created a parent index hierarchy, and ideally what I wanted to do, I didn't quite get to it, pass in identity matrices for any basically bones that should be firing blanks, because the GPU will just start processing on a random bone rather than the bone that we want, whereas on the CPU side, we're in control of which bone we start processing first at the root. You need to make sure that everything has reference to its root node. So in order to keep our table aligned, because again, this is parallel processing, it has to be consistent, we want to pass in identity matrices here. These if statements are never a good thing to do on the graphics graphics processing unit, but unfortunately, again, time is short. I just want to get something working and then clean this up later. Ideally, it would reference back to an additional, basically null object bone that would act as an identity matrix. So it would basically be firing blank calculations after it started on a random bone and iterated all the way up to its root parent. So after this information is done, we would pass this to the vertex shader. And you can see here the data that's coming in. You would get the bone world inverse matrices as the in buffer. This is the data that's going to be passed out to the fragment shader. It's the const color. This is more of the inverse Wibbit MIPI because OpenGL does their calculations in reverse. We need to reverse these in our shader as well. This is all test data down here just to try and tweak things a little bit. But one thing that I noticed that Feingold had that I didn't, based on his research demos, he had a lot of lighting and normalization effects. I just kind of took some of that stuff out. Same thing with the texture stuff. I tried to map it as similarly to my CPU skinning shader as possible. We pass this to the fragment shader, and all it does is it just sets the out data as the fragment shader's color that we passed in. And then this gets sent back out to the rendering scheme. So what it should do is render to the screen, but that is not happening. Also, frustrating enough, again, I just ran out of time. One thing that we can do here just to get this to render, just something clean and dirty. If I were to just uncomment this private slow process CPU, this would work. So I'll show you that right now. So if I uncomment this, interesting enough, this funnels everything to the private slow process CPU. So it's, in addition to trying to run this on the graphics processing unit, it's running this on the CPU as well. And you'll see the actual skinning for the Teddy still work. So like I said, I took out the instancing of the humanoid. I also took out the skinning. I just wanted the skeleton to work. So that is essentially it. For compression, I had debugged a bit of a session with Feingold as well this past Friday. I didn't quite get a chance to work it into my own system, but essentially you are just comparing a couple different frames before you pass them in out of your converter, and you're seeing which ones are similar enough that hit that tolerance so that they can be removed. We kind of did some debugging with the SDL, but unfortunately I didn't have enough time to get that working into my own system. So I hope you enjoyed this. Like I said, I'll probably have a lot more of this working by the end of this week. I won't feel comfortable until I get some of this going, but again, we're a little pressed on time. Thank you.